So welcome back from spring break. Today we're going to start in Math 3 with looking at inverses. Now, before spring break, we looked at invertibility using the vertical line test, the horizontal line test. As a quick refresher, the vertical line test indicates if something is a function or not, and the horizontal line test indicates if something is invertible. Okay, so let's look at some functions and see what they look like with their inverses. So the first thing we're going to look at is x squared, okay? Now, the deal with x squared, though, if we graphed x squared, as a quick reminder, we'd see that it looks something like this. And if you remember from last week with our horizontal line test, this is not invertible, okay? Because it would cross through two spots if you did a horizontal line test. Okay. However, what you can do with these problems is you can restrict its domain. So that's what this says right here. We're restricting what x can be. We're saying x has to be greater than or equal to 0. If we do that, we can make this function invertible. So let's look what it looks like. So we have some points based on our values of x being bigger than 0 or equal to 0. So we have 0, 0. So let's plot these points. We have 1, 1. We have 2, 4. We have 3, 9. So our graph looks like this based on the fact that let's make that bigger. Based on the fact that we have restricted its domain. Okay. So if we look at this, we have the function is y equals x squared. Okay, the domain is looking at all the x values that exist. Well, we have our domain, it's right here. So it's going to be, if we write it out as an interval notation, it's going to be, that should be a bracket. It should be 0 to infinity. That's the only thing we can use, because if we start using the negative values, it becomes not invertible. For the range, we're looking at the y values that can exist in this problem, and again, we're going to have 0 to infinity. Okay, so now let's look what happens if we invert this. Okay, so to find the inverse of a function, what you're going to do is you're going to switch around the x and the y terms. So we're going to rewrite this as x equals y squared, and then what we're going to do is we're going to solve for y. To do this, we're going to take the square root of both sides to get rid of that squared on that y, and now you have y equals the square root of x. Now this little -1 sign here, that tells you, it's a special thing for math, it tells you that this is an inverse function. Okay? All right. So, now if we look at this, all right, we're still being restricted for a specific reason. So if we put 0, 1, 4, and 9, I'll get it. Okay, we'll get the y values of 0, 1, 2, and 3. Because what we did is we square rooted all the x terms. You can see what we did is also with the values in our chart, we took the y values here and made them the x term values. Okay, all right, and then the x term values became the y values. All right, so this is what happens when you do an inverse. You switch the values around. So our invertible function is the square root of x, and what we have to do now, we also have to say that x has a domain restriction of greater than or equal to 0. Okay, so let's graph what it looks like now. So if we use our points, we have 0, 0, we have 1, 1, we have 4, 2, we have 9, 3. So it looks like this. So that's our new graph of our inverse function. Okay, if we're looking at the domain, okay, we're still using interval notation. It starts at 0 with a bracket and goes towards infinity. And the range is the same thing as well. It starts at 0 going up. As it goes to the right, it still goes up. It's just not as fast as it used to be. And it goes towards infinity. So that is all the even functions. That's what you're going to look like when you're doing these types of things. Okay, when you're trying to find an inverse using a graph or a table. Okay. So now let's look at this with cubic functions. With our cubic function, all right, we have y equals x to the third. You can see the table there. So we're going to plot those points on the table. So we have -2, -8. We have -1, -1, 0, 0, 1, 1, and 2, 8. Okay, so our graph will look like this. Now, this doesn't need domain restrictions because it's already invertible. Okay, if you remember again from last week, the odd degree functions are invertible, the even degree functions are not, unless, of course, like we looked at the top part, where you restrict the domain. So that's what the x is greater than or equal to 0 is for those problems. Well, you don't need a domain restriction for the odd degree functions. So our function is y equals x to the third. The domain, all the x values that exist in this function are from -infinity to +infinity. All the x values exist in this function. And the range is the same thing. It goes from -infinity to +infinity. Okay, now let's check out the inverse of this function. So like before, to find the inverse, you're going to switch around the x term and the y term. And you're going to solve for y. So we're going to take the cube root of x. So now we have y. I'm going to put that little sign up there to signify that it's an inverse. Okay, and we have the cube root of x. Okay, so when we look at these values, we're going to again switch the x's and the y's from the original table. So we have x is -8, -1, 0, 1, and 8. The y values will be -2, -1, 0, 1, and 2. Okay, so again, our x and y values switched in our table. So when we go to our invertible function, all right, we have the inverse of y is equal to the cube root of x. Okay, and let's plot these points. So we have -8, -2, -1, -1, 0, 1, or sorry, 0, 0, 1, 1, and 8, 2. So basically what this graph has happened is this graph has been flipped on its side. It's fallen over, and it can't get up. Okay, the domain. So the domain is what x values exist in this graph, this new inverse. Well, all of them. So we're going to have -infinity to +infinity. And what the range value is the y values that exist in the graph. Again, going from -infinity to +infinity. And there you go. Okay, so now this is going to be applicable to all the different degrees that you're going to see, which is what we're going to look at now. Okay, so you have x to the fourth. Okay, if we find the inverse of this, we're going to switch the x and the f of x out. So it's going to be inverse is going to be the cube root of, the fourth root of x. There we go. But because it's an even degree, it's not invertible unless you restrict its domain. So the domain has to be, x has got to be greater than or equal to 0. Okay. For odd degree functions, like we just did with the cubic function, you don't have to restrict the domain. So our inverse is going to be the fifth root of x. Okay, because if we switch the two x and the y's, we just have the fifth root to get rid of the fifth power, and there is no domain restrictions. Okay, for f of x equals x to the sixth, the inverse of y rather, the sixth root of x, and again you have to restrict its domain because it is an even degree function. Okay, so this can happen for anyone. It doesn't make a difference what the numbers are. We can see that as we get bigger and bigger. X to the seventh, the inverse will be the seventh root of x, and there are no domain restrictions because it's an odd degree function. Now we're getting to crazy numbers. X to the 57th power, the inverse is going to be the 57th root. Oh, that was ugly. Here we go. Of x. Because it's an odd degree function, there is no domain restrictions. But the last one, 314, that is an even degree function, because 4 is an even number. So we have the inverse of y is equal to the 314th root of x. and x has a domain restriction of greater than or equal to 0. Okay, so that's going to be happening for any different degree function you have, whether it's odd or even. The odds do not have domain restrictions, and the evens do. Okay, all right. Try the practice, and then make sure you ask questions if you have questions. All right. Good luck.